Now let's do some waves and sound homework problems. The formulas for this unit are very straightforward. Remember, we talk about period and frequency. With period, we use a capital T, and it's quite literally the total time you're given divided by the number of cycles. And frequency, we use an F to symbolize frequency, and that's the number of cycles divided by the total time. Important thing here is they're reciprocals of each other. Period is 1 over frequency, and frequency is 1 over period. I don't care which one you use. But remember, period's always measured in seconds, while frequency is measured in hertz. The basic wave formula is V is F lambda, where V is the speed. All right, F is a frequency in hertz, and lambda is the wavelength. Remember how to make a lambda. Make a kind of a curve, and then a leg. Okay. Now we have one problem in this section that's, we're talking about waves on a string. Now, this one might be a little confusing. If you have a wave on a string and it's at its fundamental, you see there's one antinode right there and 2 nodes. It's vibrating up and down. This is like when you pluck a guitar string. All right, the frequency is going to be given N, where you're counting the number of antinodes, so in this case it's 1, the speed of sound in that medium, divided by 2, and L is the length of your string. So, or length of your tube, depending on which one. Now, suppose I have a piano player plays a note A at a frequency of 440 hertz. So I know my frequency is 440 hertz. What is the approximate wavelength of sound, of this sound wave, if the speed, all right, is 340? So I know the velocity is 340 meters per second. And what is the wavelength? So we're looking for wavelength. So here's my givens, my unknown. The equation is V is F lambda. Now remember, an equation has to have an equal sign, and you have to be using symbols. Don't write it out. Okay? So I'm going to solve this. I'm looking for wavelength, so I'm going to divide both sides by F. So lambda is V divided by F. So the wavelength is the speed, which is 340, divided by the frequency, which is 440. And that gives me 0.7, let's see, 340 divided by 440. It's 0.7727. Let's call 773. And don't forget your units. An ocean wave has a frequency of 2 hertz, so that's my frequency, and a speed of 20 meters per second. So that's V. What's the wavelength? All right. So in this case, the frequency is 2 hertz. Velocity is 20 meters per second. And we're looking for the wavelength. This is just like the first problem. My equation is V is F lambda. So my frequency, oh, I don't want frequency, I want wavelength. Wavelength is V divided by F. So this is 20 divided by 2, or 10 meters. A tuning fork has a frequency of 280 hertz. That's my frequency. With a wavelength is 1.5 meters. That's my wavelength. Calculate the velocity. So I have frequency is 280 hertz. And the wavelength is 1.5 meters. Calculate the velocity. V equals F lambda. So I'm looking for velocity. Don't forget your unknown there. So it's 280 times the wavelength, which is 1.5. That's 420 meters per second. Now a wave moving along a rope has a wavelength of 1.2 meters. So that's lambda. And a frequency of 4.5 hertz. How fast is it moving along the rope? Now, how fast is velocity? So, givens, I have wavelength is 1.2 meters. Frequency is 4.5 hertz. And I'm looking for the velocity. Equation, V is F lambda. So it's 4.5 hertz times the wavelength, which is 1.2 meters. That's 5.4 meters per second. Okay, a jump rope is shaken, producing a wave with a wavelength of 0.5 meters. So wavelength is 0.5 meters. With the crest of the wave passing a certain point 4 times per second. And I told you that that's 4 hertz. So that's the frequency. It's 4 hertz. What is the velocity of the wave? So my equation is V is F lambda. So this is 4 hertz times 0.5 meters, or 2 meters per second. Now a wave has a period of 6 seconds. So period is 6 seconds. What's the frequency? Well, I know I want the frequency. And I know the frequency is 1 over the period. So the frequency is 1 over 6, or 0.17 hertz. Now it takes 3 seconds for one complete wave. So 3 seconds, so the total time is 3 seconds, and the number of waves is 1. What's the period and the frequency? Remember, the period is the total time divided by the number of waves. So this is 3 divided by 1, or 3 seconds. You could have just read it off there. Now for the frequency, I know the frequency is 1 over the period. So it's 1 over 3, or 0.333 hertz. 2 answers. The amplitude of a wave is doubled. How much more energy does a wave have? You remember, the energy in a wave is proportional to its amplitude squared. So if I were to double the amplitude, and we're going to pretend like those are doubled amplitudes, amplitude is proportional to the energy, or energy is proportional to the amplitude squared. So let me rewrite that. Energy is proportional to the amplitude squared. So if I double the amplitude, the energy is 4 times, because 2 squared is 4. So this wave right here, if that is twice the amplitude, this wave carries 4 times the energy of this wave. Redraw and label the wave with the amplitude, crest, trough, wavelength, equilibrium line, and what kind of wave is this? Okay, I'm going to blow this up really big. All right. The first thing they want is the amplitude. Remember, the amplitude is from the equinodal line. This right here is the equilibrium line, so I'm going to go and write an equilibrium. It's this line right here. All right, it's the whole line. All right, tell you what, I'm going to cheat and just actually change that color to blue. Okay, so the equilibrium line is in blue. Now, the amplitude, oh, I guess it's now red. All right, so now let me go back to my pen. Now I'm going to do the amplitude in blue. The amplitude is the distance from this equilibrium line to a crest or to trough. So AMP. All right, these are amplitudes. Any one of these, and this is, let's do this. Let's just do an arrow. The amplitude is from the equilibrium line down to a crest or trough. Okay, what is a crest? All right, a crest, we're going to do this dark blue. It's one of these peaks. It is a point. So put an X or a dot. A trough is at the bottom. So let's do that one in pink. Trough, we're going to do it in pink. It's down here. Trough, T-R-O-U-G-H, down at the bottom here. Now you only have to label one of these. A wavelength. Remember, a wavelength is from crest to crest or trough to trough. So one wavelength is from crest to crest. One wavelength. A wavelength is a distance. All right, you could also go from trough to trough. It doesn't matter. You can go from, you can make one complete sine wave, but I wouldn't do that. Because unfortunately, what students tend to do is they'll only do half of it. So this is also a wavelength. But you have to make sure you get in one crest and one trough. This is another way you could have written this. All right. So if I ask you to do this on the test, I'll only want one crest, one amplitude, one wavelength, one trough, and of course the equilibrium line. Hey! Oops, wrong way. Now, sketch and label a diagram showing 6 seconds of a transverse wave. There's a period. Oh goodness, don't know what happened there. Getting carried away. 6 seconds of a transverse wave that has a period of 3 seconds. So the period is 3 seconds and has a wavelength of 15 centimeters and an amplitude of 10 centimeters. What's the speed of the wave? Well, let's go ahead and do the calculations. If the period is 3 seconds, then the speed is f lambda, but you remember f is 1 over the period. So that's lambda divided by the period. The wavelength, goodness, is 15 centimeters divided by the period, which is 3. So this is 5 centimeters per second. You could also convert it to meters per second. Now I want to show 6 seconds of a wave that has a period of 3 seconds. So if the period is 3 seconds, I need to show 2 wavelengths. So since, let me put this in another color, since t is 3 seconds and I want to show 6 seconds, that I need to show 2 periods. So this is 2 periods. 1, 2 complete periods. It has a wavelength of 15 centimeters. So the wavelength is from crest to crest or trough to trough. So this is 15 centimeters. Now, you can do this any way you like. This right here is 15 centimeters. So this is 30 centimeters to do it correct. And this is 0 centimeters. This is a correct way to put it on the graph. It has an amplitude of 10 centimeters. So the amplitude is the vertical distance from the equilibrium line to the top. So this is 10 centimeters. And this is negative 10 centimeters. Because remember, the amplitude is measured here. Have we done everything? Sketch and label a graph showing 6 seconds of a transverse wave. That's a period of 3 seconds and a wavelength of 15 centimeters. Yeah. Now, if this were a time graph, this, of course, would be 3 seconds, 6 seconds. Let's see. Now, Lupert skipped to school one day and went to Lake Conroe. Oh, goodness, he's bad. While he was sitting on a dock reading his physics book, because that's what you do when you skip school is read your physics book, a motorboat came by. He noticed 3 crests reach the dock every 5 seconds. So the number of crests is 3, and the total time is 5 seconds. Did you see how I read that? See, every 5 seconds gives me 3 crests every 5 seconds. So this is the number, and this is my time. It's not my period, it's the time. And that the distance between the crests was 2 meters, so that's the wavelength. Calculate the velocity, period, frequency, wavelength. Okay, let's do the period first. Period is the total time divided by the number of crests. The total time is 5 seconds divided by 3 crests, or 1.2. Let's do that one again. That's what happens when you try to cheat a little bit. 5 divided by 3 is 1.67. All right, the frequency is 1 over the period. Or you could put it as a total number of crests divided by the time. It doesn't matter. So this is 3 divided by 5, or 0.6 hertz. Goodness, I'm getting off on an angle here. All right. The velocity is f lambda. The frequency is 0.6. And the wavelength is 2 meters. So this is 1.2 meters per second. Hard to believe you could get all of this out of that story. How long should a string be in order to produce a standing wave with 9 antinodes? All right. Now this is that equation we discussed before about the wave on a string. This is probably not the first homework assignment, so feel free to skip this one. But the number of antinodes is 9. So we've got this situation right here. Here's my equilibrium line. 1, 2, 3, 4, 5, 6. Goodness, we're going to pretend like there are 9 there because I'm out of room. Okay. Using a string vibrator of 180 hertz. So the frequency is 180 hertz. If the tension is adjusted, so the speed is 34 meters per second. And we're looking for L. Now, you remember the formula of Fn is NV over 2L. So I'm going to clear my fractions here. Multiply by 2L on both sides. So 2L Fn is NV. We're looking for L, so I'm going to divide both sides through by Fn. 2Fn. So L is NV over 2Fn. Now in this case, N is 9. So this is going to be N, which is 9. V is 34. Divided by 2 times 180. Now go on and multiply your numerator. 9 times 34. So this is 306. Now multiply 2 times 180. Let's try that. 2 times 180. Having trouble multiplying. It's 360. I knew that. Just kidding. All right. So 306 divided by 360 is 0.85 meters. Remember, multiply straight across the numerator, straight across the denominator, and you won't get confused. Now, Lupert skipped school again. This time he saw a boat make waves in the water such that 5 crests, so that's a number, reach the dock every 6 seconds. This is my total time. The distance between crests is 3 meters. So that's lambda. Calculate everything again. Okay. So the number of crests is 5. The total time is 6 seconds. And the wavelength is 3 meters. So let's find the frequency. Frequency is the total number of crests divided by the time. So it's a number of crests, which is 5 divided by 6. Now 5 divided by 6 is 0.83 hertz. All right, period is 1 over frequency. So, or you could put it as the total time divided by the number. It doesn't matter, you'll get the same answer. If I just do 1 over 0.833, if I do 1 over 0.833, I get 1.2 seconds. If I do total time, in this case the total time is 6 seconds divided by the total number, which is 6, I get 1.2 seconds. So you get the same answer either way, it doesn't matter. Velocity is f lambda. So the frequency was 0.833 hertz times the wavelength, which is 3 meters. Now, if you've left these numbers in your calculator exactly, you get this is 2.5 meters per second.